So folks, in the previous video, we looked at the fact that every m by n matrix can be thought of as a linear transformation. That is, the m by n matrix will take vectors from Rn and map them to Rm. That ordering always seems a little confusing at first until you think about how we do matrix multiplication. My m by n matrix is going to take this n by 1 column vector and map it to this m by 1 column vector. And so here we looked at a very concrete example where we were taking vectors from R3. This is my real vector space R3, and mapping those vectors to real vectors in R2, our R2 vector space, by this what? By this 2 by 3 transformation matrix. So again, every m by n matrix, and these could be the same dimensions. We could be mapping from the same space to itself. This could be a 3 by 3 matrix or a 5 by 5 matrix. But every matrix then is itself a linear transformation. The maybe more surprising fact is that every linear transformation from one vector space to another can be represented by an m by n matrix, where n is the dimension of my domain space and m is the dimension of my range space. So let's say that again. Let's say let T be a mapping from V to W, and let this be a linear transformation. Not just any mapping from a vector space to another, but specifically a linear transformation where the dimension of V equals m, that was an n, and the dimension of W equals m. Then there exists an m by n matrix A, so that for any x, y ordered pair, where my transformation takes the first vector x to the second vector y, where x is living in the original vector space and y is living in the range vector space, we have that a vector x is equal to vector y. That is, this m by n matrix right here does the same thing as this transformation. And folks, I think you should be a little bit skeptical about this, that every single linear transformation can be represented with an associated matrix. And to show you maybe a less commonly thought of example, I want to show you how our derivative operator, we've said before that taking the derivative is a linear transformation. The derivative of one function to another is a linear transformation. I want to restrict ourselves to the case where we're looking at taking the derivative of quadratic functions by this derivative linear transformation. And if you remember from Calc 1, when you take the derivative of a polynomial that can be written as a quadratic function or a function of degree 2 or less, when you take that derivative, you're going to end up with a polynomial that can be written in terms of degree 1 or less. So let's go ahead and come up with a matrix that actually does that for us. So again, we've got this transformation T, which maps from P2 space. What is P2 space? Again, that's the space of polynomials that can be written in terms of degree 2 or less. If I don't have the or less, it's actually not a vector space. To the space of linear polynomials. These are all the equations that can be written in terms of degree 1 or less by T of this polynomial, some f of x, that lives in this space is equal to f prime of x. So here's a transformation that how do you take a vector from P2? Well, we could take, for example, we could take this function 3x squared minus 6x plus 7, and the transformation is just the derivative transformation, and so that would give me 6x minus 6. This transformation right here can be written with an associated matrix. There is a matrix that will do this for us. Let's go find it. So before we do that, let's think about this space P2. We've said in class before that this is a vector space of dimension 3, and we can actually write out a basis for this. It has a basis, it has actually many bases, but it has a basis, the canonical basis is to talk about this set right here, which has x squared 0, 0, comma 0x0, comma 0, 0, 1. That is, every single vector in this space, which is a polynomial that can be written as a degree 2 or less, can be written as a linear combination of these two vectors. So for example, this polynomial right here is really just 3 times the vector x squared 0, 0 minus 6 times the vector 0x 0 plus 1 times the vector 0, 0, 1. So I'm writing this quadratic polynomial as a linear combination of the basis of this vector space. So more importantly, that means we can go ahead and make a connection between this vector right here and just the vector 3 minus 6, 1. So here's our vector that stands for this polynomial right here. So more generally, we could take a vector, the vector that looks like a, b, c. This is a vector in P2. If you can't see that, that's the vector ax squared plus bx plus c, which is my generic polynomial function. So what we want to do is we want to come up with an n by n matrix. In this case, let's see here, we're going to take a polynomial from P2, that's a 3 by 1 vector, that vector lives in dimension 3. So this would be this generic vector here, and we're going to multiply this by some matrix to give us a new polynomial that lives in P1. This is the space of all functions that can be written as linear functions. They look like, using new letters, maybe they look like mx plus n, just using new letters. That's what all of my linear polynomials living in this space can look like. So there is a matrix here. Let's see, this is going to be a 2 by 1 matrix, a 2 by 1 column vector. So what's this matrix dimension going to be that's going to map me from this 3-dimensional space to this 2-dimensional space? It would have to be a 2 by 3 matrix. And let's actually state what that matrix is that takes the derivative. So that matrix would be, in fact, 2, 0, 0, 0, 1, 0. This is that 2 by 3 matrix that represents the operation of taking the derivative. And let's convince you of this. If I actually do this matrix multiplication, when I multiply this row by this column, I get 2a, and when I do this row by this column, I get the number 1b, or just b, and that's precisely what we do when we go to take the derivative. That is, another way of saying that is if I were to take the derivative with respect to x of this polynomial right here, I'm saying that we can take that derivative by taking 2, 0, 0, 0, 1, 0 times the vector a, b, c, and if we do so, we end up with the vector 2ab, but that just corresponds to the polynomial 2ax plus b, and that is, in fact, the derivative of that vector. So folks, this may not be the most efficient way to do calculus, but because the derivative is a linear transformation, and we've looked at that in previous examples, because the derivative is a linear transformation, that means we can find a matrix that does that same operation. And there is an example of it when we think of taking the quadratic polynomials, taking their derivatives, giving us these linear polynomials. Folks, you could actually extend this idea, but it becomes impossible to write out. We've said that the space of all functions is a vector space and that the derivative is a linear transformation. And so you could come up with an infinitely large matrix that does the derivative operation for you. And that's something you could think about if you want, although it makes my head hurt a little bit. So the big point here, folks, that maybe you didn't believe, and maybe you still don't quite believe, but the surprising fact is that every linear transformation from one vector space to another can be written with a corresponding matrix. And just to give you an example of that, I showed you that the derivative linear transformation, which we've seen before, can be represented by this matrix right here if I think about taking the derivative of a quadratic and mapping it to a linear function. So folks, I hope that was helpful. In the next example, we're going to continue to just look at how this morphing of spaces happens with these n by n matrices. Thank you very much.